Get started. Get started. Get started. Let's get it started. Let's get it started in here. Let's get it started. Let's get it started. Get it started. Let's get it started in here. Let's get it started. Let's get it started.
So let's state it. Let's get it started. Ha! Okay, I can't sing. This, what we're about to start, is what's called chi-squared. And there are a bunch of different chi-squares, but right now, we're going to be talking about the chi-squared goodness of fit. You saw the dice. We're going to be making dice tomorrow. So, be ready. Now, what a chi-squared, first of all, what we've been working on in the past is we've been working on quantitative data. So, looking at the number of pounds, the number of days. Okay, but what we're about to do right now is we're about to discuss, and this should be a period, categorical. So what categorical would be is categories of animals, categories of students, freshmen, sophomore, juniors, and seniors. Quantitative is the quantity, so the number of freshmen that we have. But when we take all the numbers, we can put them into categories. And as you can see here, as we're working on the categorical, one thing that we're concerned about, our HO is the distribution as stated. Well, isn't that consistent with what we've done? But now our HA will always be not equal to, for when we are doing what's called the chi-squared goodness of fit. And the reason that we do, first of all, with the chi-squared goodness of fit, it is, as you can see here, we have it's going to be a one-way table. And the reason it's a one-way table is because we're looking at a single category. And I just wrote down a couple of examples of a single category. Well, we have the M&Ms. Well, we have one type of M&M, but how many different colors are there? I want to say there are 5, but you can correct me tomorrow if I'm wrong. Skittles, truly don't know. You can tell me that tomorrow, how many flavors they have. In terms of, we have here one category of animal. Well, here, one category, we have types of dogs. Okay, that's one category. Types of nuts, types of cats. So that is an example of categorical. So as I look here, what is chi-squared goodness of fit? What we're doing is we're always, it allows us to analyze the sample data when placed in a single category. And what that looks like is, let me show you a perfect example of something you guys are totally addicted to, your M&Ms. So we have 30% brown, 20% yellow, 20% red, 10% orange, 10% green, and 10% blue. So I said that there were 5, okay, like I said, self-corrected, there are actually 6 categories. But this would be an example of a distribution. Next, what does the chi-squared look like? Well, first of all, the whole purpose for it is that we are checking the distribution to see if it differs from the claim or from the expected. Well, isn't that what we've been doing before? And actually a chi-square, the actual diagram looks something like that, which we're going to be discussing a lot more in a minute. What is the null hypothesis? Well, the thing about the null hypothesis is that it's going to look different from what we've done before. It is, as you can see right here, I've stated that it's in words. And as always, we're assuming that the HO is true. So we haven't said anything any different. But what is different is that your HO, again in words, is the company's expectation or the client's expectation. So it's the stated distribution about the categories in the population. And we are confirming that it is correct. Again, the status quo. One thing that I wanted to mention that I may have forgot to mention up here, and I think I actually did, we're checking to see if distributions differ. Well, I showed you M&Ms. Also, here as we look at the idea of Skittles. Skittles has, correct me tomorrow, 5 flavors. They're equally distributed. M&Ms, and I have M&M Blue. I was about to write down what the different M&Ms are, but as we can see, I already mentioned it. We have all the different colors, and this is an example of, again, the distribution for the chi-square. So now our question is, we've talked about the HO, what about the HA? The HA is our claim. We're saying, nope, you're wrong. The distribution of the category variable is not correct. You are wrong, company. You are cheating me. Okay? Again, as always, we're saying that something is off. As we do this, one thing that we want to get into math mode quite often, but the one thing we have to be careful of when we say this, we don't want to state the alternative hypothesis by using math and saying all the proportions are wrong. So we cannot say proportion 1 is not equal to proportion 2, et cetera, et cetera. And in reference to the M&Ms, we can't say the proportion of red is not equal to the proportion of green, which is not equal to the proportion of yellow, and et cetera, et cetera. And the reason we can't is because, as I flip back to the chart, they already are not equal. So how are we going to say that how are we going to utilize that information if from the start the company is saying, this is a customer favorite, so that's why we go with the 30%, and here the 10%, I guess, are the least favorite. I'm wondering how old this is, because aren't there blue M&Ms now? But we're going to stick with what we have here. So as we get into the meat of the chi-squared distribution, what is the observed values? Well, the observed values, the observed counts are the same as the actual ones, the observed ones, the ones that you physically see, the ones that as you are opening up a bag of M&Ms, you see that you can count 5 reds, you can count 5 greens, you can count 20 yellows. Okay, I guess they got a little heavy-handed on that one. The expected count is here the percentage of the data that the company or we expect to occur. So here, as an example, going back to the M&Ms, and I'm looking at here the milk chocolate ones. Let's say that I opened a bag of M&Ms and found that there were 100 pieces. Okay, so they've stated that we have 30% brown, 20% yellow, 20% red, et cetera, up to 10% blue. So in that particular bag, I am expecting out of the 100, 30% to be brown. So what is that? I'm expecting 30 of them to be brown. Okay, in that one bag of 100, I'm expecting, can't read my own writing, what is that? 20% to be yellow. So here, again, 100 times 0.2 is 20%. And of the red, 20%, which means it's going to be 20. And then if the orange, just doing the math, the green doing the math, and then the blue doing the math. And if you add up all of those, of course it's going to total be 100 pieces. This is an idea of how we find the expected count. Now I chose a nice even count of 100 in a bag, just because you can do the math without thinking on that one. But what if it was like 101 pieces? Well, some of you guys have a serious tendency to round. Never round when it comes to expected count. And the whole premise is, you can read this here, but their ideology is if you're rounding it, you truly don't understand that the expected count is the average number of observations. Because we don't want to, YJLP, we don't want to lose points. Now let's talk about the conditions of the chi-square value. Okay? Bye-bye. You should have texted me. Okay, now, I'm sorry, guys. That was one of your fellow classmates confirming something. Okay, so our question here is, what are the conditions that are needed? Well, randomness, I mean, isn't that the mantra of statistics? Here, the 10% count, again, we're trying to make sure our sample size is not excessively large. And now here's a little different. It's still a large count condition, but we're not looking for normality. We're trying to make sure that our sample size is okay. Our large count is that we have to look at all the expected counts, not the observed, the expected. We haven't even talked about how to find that yet, but we will. All the expected counts have got to be greater than 5. Okay, now we're going to do that in a minute, but before we start using it, there's a couple of things that we have to remember. Okay, don't try to perform the observed and the expected, putting both of those in the calculator. Remember, the expected count must be calculated or found for us. So that's number one. Number two, for the LCC, remember we have to examine the expected count. Not what we observed, but what we've expected. Which takes me to, what is the expected count? Well, let's talk about what the chi test is, and then we'll see how expected count chimes into that. So here's the chi-square statistic, and the chi-square symbol is right there. There's your Greek. And the chi equation is the summation of the observed minus the expected squared divided by the total number of expected. As we look at our values right here, sorry how that ran into my graph, but our P value is over here, and our chi value, our chi statistic that we're going to calculate is what's over here. The value right here is our chi, and the value right in there is our P. Just like a T, we have a degree of freedom, and the degree of freedom is k minus 1, in which k is the count, or I should say the number of variables inside the category. So the number of variables in the category. So in other words, as I'm going back to the M&Ms, how many were there? 1, 2, 3, 4, 5, 6. Yeah, I can count. So there's 6 of them. So in this one, the degree of freedom would be 6 minus 1, which is 5. They don't use n, but if you give me n by accident, oh well, just know that it's minus 1. Now, one thing about the chi-square is, you know how for the normal distribution and how for the t distribution, the shape is the same for all z's and all t's, even though z's and t's look alike and they have a slightly different variation. Well, I already showed you how jacked up the chi looks, but it doesn't always look like that. So for that reason, a chi-square here is a family of density curves. Your chi-square distribution is going to be right skewed, but the shape varies based on the degree of freedom. So as you look over here, look at all these different chi-squared. I don't know if you see that that's the degree of freedom was of 5, which means our number of variables we looked at was 6. Okay, so that means here k was equal to 6. Here that means k was equal to 11. And here k was equal to 16, because you can tell that that's a 15. And notice how they get bigger and bigger and bigger. It does what? It looks more normal. But takes a lot of time. But doesn't that seem like that's what happens too often? Okay, now as we wrap up this page of notes, okay, how do we find our p-value? Because here we've talked about how to find chi, or have we? We talked about in generalities how to find it. So now we have to find a p, and we find the p-value, I should say, with the chi distribution, just like with the t distribution. You find the chi on your chart. Remember, you're looking at that chart that has chi squared on it. Here is going to be your chi squared value inside the body of it. There's your degree of freedom, and up here are your probabilities. So Hannibal Lecter, just like the t. Okay, in the calculator, we can find the p-value with the chi-squared PDF. And oopsie, not PDF, CDF. Now, for the 83 and the 83 plus, at least those are two I know, and Casio, you are on your own. Google it. You're going to be using the chi-squared CDF, not P, CDF. It's the left bound, that's an L. Some huge number, and the degree of freedom. This is going to be consistent all the time, because let's face it, as we slide back up here, your chi is going to always be here, and over here is your positive infinity. But for the 84, you can literally just key it in. It does all the math for you, so you don't even have, it gives you the chi-square value, etc. Us 83 plus people, or 83s, we got to do it on our own, but at least we don't have to use the chart if we don't want to. Okay, but for the 84s, here you're going to go into stat, go over the test, go down to chi-square GOF, that specific one, and then from there, okay, follow the guides of what the 84 tells you to do. So right now I want to do a complete problem. And I kind of answered the question, what if I don't have a GOF test on my calculator? So here I went, okay, so remember to find the p-value. You're going to go, why am I doing T right there? Chi, CDF, left bound, positive infinity all the time, because that's what your right bound degree of freedom. But for those of you who have 84s and 84 pluses, be ready to help each other out tomorrow. In terms of the actual math, though, we have to do it the long way if we don't have the calculator. So please take a minute to read over this scenario. Okay, welcome back. So here, this casino apparently has, out of the 38 slots, it has here 18 red, 18 black, and 2 green. I know nothing about gambling, so I don't know the significance of that, other than that's how roulette wheel is designed. Okay, but on one table, this is the actual display. So our step one is to state the appropriate hypothesis test. So remember, the casino is saying this distribution is as stated. That they said the probability of a red is 18 over 38, probability of black is 18 over 38, and the probability of green is 2 over 38. So again, this is the casino's, forget expectations, that's how many on the wheel they have. This is what the casino has, okay? Now, our HA, we're saying at least one of those probabilities are off. Because one could be off, but the other two could still be right. So that's why they say at least 2 have got to be wrong or incorrect. Now let's get to calculating the chi, the expected count. Remember, you have a random sample of 200. So your expected red, if it's 18 out of 38, which is what they have up here, that means your expectation is going to be whatever that percentage is times 200. Because remember, right here, we're saying 18 out of 38 are going to be red. Okay, now as we look at the black, they say 18, again, out of the 38 are going to be black. And then finally, they say here that 2 out of the 38 are black. So that's where I got these values from right here. For the red, for the black, for the green. So that percentage, which is 18 divided by 38, should have done this before. We're saying that that's 47%. Now I'm choosing not to use percentages because I'd have to round and that's going to mess me up. Because this decimal, it just goes on too long. But they're saying here that 47% of the 200 is going to be red. And then they're saying that for the black it's the same. 47, again, 0.368 are red, are black. And then of the green, we're saying that out of the 200, they're saying that 5%, so 2 over 38, which is 0.0526, are green. Okay, so now that I have that stuff, now I want to put in the chi value. And as I put in the chi, I want to do the math. Remember, this is saying take the sum after I've done everything. So here's the observed, which is right here. And then we have the predicted. So here, the observed, and there's the predicted that I have right here in the orange. Here is the predicted, or the expected, expected, predicted, same premise. And here's the expected. So here's the expected for the red, expected for the black, expected for the green. These values right here, the 99, is what we have observed. There is 99 out of the 200. We observed that there is 16 out of the 200 that were green. So as we do the math on here, unfortunately, we go 85 minus, so you have the observed minus the expected, square it, and then divide by 94.74. Here, you've got the observed, we're looking at the black now, minus the expected, now square it, and then divide that by, again, the expected. And you've got the observed minus the expected, square it, and then divide that by the expected. You wanted your math, you got it. Here are the values right here, and that is your chi squared. Now, again, if you've got an 84 plus, I don't know about TI Spire. You've got to figure that out. It does the math for you, but for us that don't have those calculators, we've got to do all this math ourselves. Okay, now as we look at problem number 6, we want to confirm the expected counts are large enough. So we need to know the degree of freedom. Oopsie, it didn't put down the degree of freedom. So the DF is going to be 3 minus 1, which is 2. And all the expected counts are larger than 5. So therefore, our condition has been met. They told us that we had a random sample. And then if we look at our 10% condition, that's applicable too. Look at our diagram for that. That thing looks kind of whacked, but that is the shape. Why? Because the degree of freedom is so small. You don't have to worry about drawing that. I just wanted to show it to you. Okay, now we're going to use our table or our chi CDF for those of us who don't already have it shown to us. So here's your chi CDF. Remember I said the lower, upper degree of freedom. This is how we're going to get our p-value. Okay, with the use of the table, we are going to be looking for, so you can see here we have our degree of freedom, which is 2. Then we are looking for the value of what? 4.03, which is going to be in here somewhere. So we can see that it's going to be between 10% and 15%. So between 10 and 15 in terms of without using the table. But if we use chi CDF, we have this. Now this video unfortunately is long, so I'm going to make this quick. So here because you have the p-value greater than the alpha, you're going to fail to reject, so we do have convincing evidence. We do not have convincing evidence that it's any different from what they claim. I will see you guys tomorrow, and let's get ready to make some dye. Bye-bye.